Hello, and welcome back to the third session of this SSC Symposium titled Anomalies in Modern Astronomy Research. We have now with us Dr. Pavel Kroupa, who will argue that dark matter does not exist, but we know where to go. He will elaborate on the hypothesis that any cold or warm dark matter particles of any mass exist, has been falsified. How many of the extragalactic problems disappear automatically without dark matter, but there's still the issue regarding which background cosmology accounts for the observed universe. Dr. Pavel Kroupa studied physics at the University of Western Australia, Perth, and defended his PhD at the University of Cambridge in 1992. After postdoctoral appointments in Heidelberg and Kiel, he accepted a professorship at the University of Bonn. Pavel leads the Bonn-Prague SPODYR group, which studies stellar population, stellar dynamics, star cluster evolution, galactic dynamics, and cosmology. The group is unique in having developed the non-LCDM structure formation simulation infrastructure, allowing physically well-motivated research on galaxies and the large-scale matter distribution. Thank you for joining us, Dr. Kroupa. You have some words before your video.
Yeah, so thank you so much. It's a great pleasure to be here, and apologies for the for the taped presentation which will follow. I understood the instructions that we should be taping that beforehand, but the presentation will be the same as if I were holding it live anyway, and it's anyway better because of the internet connection, as I'm now at home, and it can become a little bit unstable once for a while. So thank you, and yeah, please start this presentation now.
Excellent. And also, please remember that Dr. Kroupa will be with us at the end for the Q&A. So
Sure.
let's get it started.
Hello to dark matter does not exist. Are we in the greatest crisis in physics ever as a consequence of that? But we do know where to go. If we set up as a hypothesis that Einstein's gravitation is valid everywhere and all matter is created in a hot Big Bang, then by comparison with observations, we are led to the necessity to introduce a hypothesis B. And this hypothesis B is that cold, warm, or fuzzy dark matter must exist. This then becomes the standard model of cosmology, which is so popular today, the SMOC. It consists of 5% normal matter, 25% exotic dark matter, and 70% exotic dark energy. This model has a peculiarity, a curiosity, and that is that galaxies become unpredictable. So if you look at a galaxy like NGC 1560, it is a rotating disk galaxy, we can measure the surface density of stars as a function of the galactocentric distance from the center, and we can measure with radio telescopes the surface density distribution of the gas. From this observed mass distribution, we can, in a good theory, hope to predict the rotation curve of the galaxy before we do observations of it. And so the question is, can we predict the rotation curve in the SMOC given such data? It turns out that we cannot, because we do not know well enough how the dark matter is actually distributed in this galaxy. So galaxies become unpredictable. Put another way, this means that interstellar space travel becomes quite impossible, because there can always be a dark matter clump that will pull your ship off course entirely. The ship with not enough fuel can then get lost, all crew starving to death. Is the real universe truly so unpredictable? Now, this standard model of cosmology can be used to do calculations to quantify the evolution and properties of the dark matter halos in which galaxies form and evolve, and how matter is distributed in space, at least in a statistical sense, even though for each individual galaxy we cannot predict the rotation curves. So according to the model, we had an inflationary hot Big Bang. The universe expands, the gas cools, forms the CMB when the photons decouple from the gas. As the universe expands, the dark matter forms the first potential wells into which the cooling gas falls, and then ultimately make stars, and so the first dwarf galaxies are born. As the universe expands, these dwarf galaxies collide, merge to make ever larger galaxies. Until today, we observe these structures with our telescopes. The universe expands ever more rapidly since about 5 billion years ago, driven by this mysterious dark energy. It's essentially a new epoch of inflation, which will tear the universe apart entirely. And so, given such calculations, which have achieved a great level of sophistication these days, we can test these robustly against observations. And so a whole number of tests has been done. I here count 8. I will skip the first one, which is still valid. None of it has gone away. None of the problems reported in these tests have gone away. And I will now concentrate on the more recent tests. So, for example, the second one is the profusion of disk galaxies as observed in the real universe compared to what we see in the computer in these calculated standard model of cosmology. So the observed universe shows us that only a small, tiny fraction, an insignificant fraction of all galaxies, more massive than 1.5 times 10 to the 10 solar masses, are elliptical. The rest are all thin disk galaxies supported by rotation. A few are peculiar, but these are interacting disk galaxies. 6 billion years ago, the picture was basically the same. The elliptical galaxies are very rare, and the majority of galaxies are thin disk galaxies with a larger fraction of peculiar galaxies, but these are thin disk galaxies which are interacting with other galaxies. So in the real universe, the vast number of galaxies are thin disk galaxies. We count about 80%, probably more. But in the standard model of cosmology simulations, they lead to too many spheroidal galaxies due to the many mergers. You take two disk galaxies and they merge, as happens in this model automatically, then you will get a rounder galaxy. And this happens typically many times for a galaxy. And so typically we would expect quite roundish galaxies. And this alone falsifies the standard model of cosmology with more than 5 sigma, as shown in this diagram. So here we are showing the distribution, the probability density as a function of the projected shape of the galaxy, Q sky. This is taken from Hasselbauer et al. Q sky is calculated as follows. We see an image on the sky of a galaxy. It has a semi-major axis and a semi-minor axis, and the ratio of these gives us Q sky is always less than or equal to 1. 1 means we have a round galaxy on the sky, and very small q implies that we have a very thin galaxy. Now the observational data, here the gamma data release 3 and SDSS data release 16 are mutually beautifully consistent, as you can see in this distribution. Of course, since even if all the galaxies are thin disk galaxies, we would expect such a distribution as shown here in the black lines, because a certain fraction will appear quite round just because we see them face on. So the calculations in the Illustris scheme, which are based on a adaptive mesh code, show that as the resolution is improved, we get more fraction of thinner galaxies, but still far too many round galaxies. The simulation shown here in the Eagle set of simulations, which are based on the SPH code with very different feedback processes to the Illustris simulations, show very nice consistency with the highest resolution Illustris simulation. So we see now that these calculations have converged, and they are significantly different to the observed distribution. There's a lack of thin galaxies in projection on the sky. And this difference is more than 5 sigma, falsifying the standard of cosmology at very robustly. And so while the model produces too many round galaxies in 3 dimensions, the real universe produces far more thin disk galaxies in reality. We can then consider the next test, which is based on Chandrasekhar dynamical friction, and we can look at satellite galaxies. So how does Chandrasekhar dynamical friction work? Well, first of all, this is a direct test for the existence of dark matter particles, which is quite ignored by the community. And It works as follows. So we have a major galaxy like Andromeda Milky Way, which has its dark matter halo around it, and a smaller galaxy falls into this dark matter halo, and then it interacts with the dark matter particles in the halo of the Andromeda Milky Way, while the galaxy which fell in has its own dark matter halo. So while it's moving through the dark matter halo of the major galaxy, the dark matter particles are deviated gravitationally and gravitationally focused behind the galaxy, which leads to a dark matter wake, and that dark matter wake gravitates back at this galaxy, causing a deceleration. Technically, what actually happens is that the transfer of momentum from the motion of this galaxy to all the dark matter particles, which leads to this wake, is responsible for the loss of momentum of this galaxy, so it slows down. The dark matter particles have a mass small m. The galaxy falling in has a mass capital M, and its velocity is Vm. And according to Chandrasekhar dynamical friction formula, this is what it looks like. We have a deceleration, you see the minus, and that depends on the velocity, 1 divided by the velocity squared. Remember, here's the velocity vector. It depends on the mass of this galaxy, which is falling in, and it depends on the mass density of the dark matter halo of the major galaxy. Now look at that it does not depend on the mass or the number density, but on the product, which is the mass density, which means the individual masses of the dark matter particles are not really important here. And this product, so the mass density of dark matter, is given by the theory. It's fixed by the initial conditions, which are the CMB and the structures we observe, so that the model has been tuned to approximate the amount of matter we see in the universe, the chemical composition of the universe, and so this number cannot be changed. And so as a consequence of this, the galaxy suffers a deceleration and gets slower. So when it gets slower, it falls towards the center of the dark matter halo of the major galaxy, and you can see the velocity vector gets smaller, and so this galaxy merges with this galaxy. So this is why galaxies merge, but only in the dark matter theory. Now, applying this to satellite galaxies, which we did in 2011 in this paper by Angus et al., we've seen that the satellite galaxies of the Milky Way have no infall solutions if they have dark matter. A more recent application to the M81 group in this peer-reviewed publication by Oehm et al. Looked at this problem. And so here we have an image of this M81 group of galaxies. We have a Milky Way type galaxy here with companion galaxies. These galaxies we know must have had encounters among each other at least once, if not multiple times, to produce this gas distribution which we see in red, which is mapped out with radio telescopes. So you see that the galaxies are nearby. That's the scale, which means they're all moving around with overlapping dark matter halo. So there's a huge amount of dynamical friction acting in the system. And Yoon looked at the dynamics of the system and found no solutions with dark matter because the system merges far too quickly. He was not able to get the distribution of gas to that extent because it just merges too quickly. The same conclusion was obtained by this American team at the same time independently. Now, these were conference proceedings, so these two groups, the Korean and the American team, did not publish these results in peer-reviewed papers because it's a hot potato. It basically means you cannot have dark matter. Now, we looked at this in these peer-reviewed publications and found that basically all members of the M81 group would have to have fallen in synchronously from large distances and have a perigalactic encounter with M81 at nearly the same time without having merged yet, and this is arbitrarily unlikely. So this completely confirms these previous independent conclusions. Now we have quite a few of these compact groups. They all should be merging within 1 billion years, and since they exist, it indicates that they have a much longer lifetime, which tells us that dark matter cannot be there. We can now also look at the bars of galaxies. Here's an image of a beautiful barred galaxy. The bar rotates like a rigid rod, And what happens is that this bar, which is a substantial amount of mass concentration, produces a wake in the dark matter behind it as it's orbiting, in a galaxy immersed in its dark matter halo. And so this dark matter wake again pulls back at the bar, slowing it down. And so it slows down in the rotation through the deceleration of through the dark matter. And so basically it means that the angular momentum of the bar is transferred to the dark matter halo, slowing down the bar. And the bar, as a consequence, shrinks in size. So we can look at the bar length in relation to the co-rotation radius. The bar tells us how fast it's rotating because it's a rigid rod, and so we can compare the bar length with the radius of co-rotation. And these are the data. So we have here the dispersion of the values of R versus the R parameter. The observed galaxies are scattered in this region here, and we can see that the observed real galaxies have R values which are small, which means they have fast bars and they are long and they fall fast. While the dark matter galaxies in the Eagle cosmological simulation have values of the R parameter larger than 3, and so they are slow. Now you can see that the 6 sigma contour and the 5 sigma contour in the data do not overlap, and this means this disjoint distribution implies that the model is ruled out with more than 8 sigma tension. So real galaxies have fast bars, dark matter galaxies have slow bars as a consequence of the dynamical friction, and this then implies that there is no significant dark matter halo in nature. So we can then look at the disks of satellites or planes of satellites problem, which is related to the structure of and correlations in the local group. So we are looking here down upon the local group from the northern part onto the Milky Way and Andromeda. This is the line joining Andromeda and Milky Way here. And we see that the Milky Way satellite galaxies, which are these circles, are aligned in a large plane of satellites, which is rather thin. There are no satellites further out. And the Andromeda galaxy, which is shown by this circle here, has its satellite galaxies, half of its satellite galaxies in a very thin plane, which points at the Milky Way. The other satellite galaxies are probably also in planes which are oriented differently. But this plane is rotating with an angular momentum pointing into that direction. This plane of the Milky Way is rotating with the angular momentum pointing in that direction, and this indicates that this plane of satellites of Andromeda is strongly correlated with the plane of satellites of the Milky Way. And this is a situation which is impossible in the standard model of cosmology, because we can ask the question, how can the Milky Way and Andromeda satellite systems be so correlated if they are subhalos falling in individually? So in the model, each of these galaxies is an individual dark matter halo which fell in independently of the others, and so they should have formed a spheroidal distribution around Andromeda. The same with Milky Way, there should be a spheroidal distribution around the Milky Way. These two should not be correlated in any way because they have their own growth histories through mergers independent of each other. And so this high degree of organization and phase space of these satellite populations relative to each other and with each other annihilates the model rather significantly. It gets worse because Centaurus A, which is a few million parsecs away from us, itself a major galaxy, has a huge plane of satellites around it. And so Milky Way and M31 planes of satellites are not unique. These disks and planes seem to be common. Wherever we have sufficiently good data, these planes seem to pop out from the sky. We can then ask, how likely is it to see 3 planes of satellite galaxies in the vicinity of the Milky Way? And based on the cosmological simulations, and one can conclude or concludes that the models are excluded with more than 5 sigma confidence. And so again, the conclusion is that the merger-driven formation of galaxies through the dark matter halos is not a real feature of the universe. Now it gets even worse than that, because the whole local group of galaxies, which is that region in space which is gravitationally bound, so outside the local group we see the Hubble flow. This local group is incredibly symmetric. And in this publication by Pawlowski et al., with the title The Discovery of Symmetric Structures in the Local Group, we look now at along the line joining Andromeda and Milky Way. We are now looking at 3 million parsecs times 3 million parsecs region. The line joining Andromeda Milky Way is here. This here is Andromeda. That's this is the Milky Way. This is Andromeda, and this is the satellite system of the Milky Way. This is the satellite system of Andromeda. And furthermore, all the other galaxies in the local group which are not satellite galaxies are these circles. They are arranged in this plane, which is very thin and has a dimension of 1.5 million parsecs with a thickness of about 50 kiloparsecs, and in this other plane, which has a dimension of about 1 million parsecs and a thickness of, again, about 50 kiloparsecs. Now, these two huge planes, which span the entire local group, are completely symmetrically distributed around the line joining Andromeda Milky Way. This plane has a distance from Andromeda Milky Way line, which is the same as the distance of this plane from the line joining Andromeda Milky Way. It is unknown how these galaxies in the planes manage to stick in these planes. They should be falling into the center of the local group, or at least orbiting in the local group. They are moving. We know that they have radial velocities, so line of sight velocities relative to us, but it seems they are moving in the plane, which is rather striking. This whole feature, this whole structure looks, if anything, like a crystal, and is moving according to this arrow relative to the CMB. So it looks a bit like a bow shock. Everything else is empty in the local group. And so this is a frightening symmetry. There's currently no known theory of gravitation which would explain this type of crystalline structure on a cosmological scale. Now, this is obviously not the standard model of cosmology at infinite sigma confidence, because nothing in this model is able to produce such a symmetry of matter on scales of millions of parsecs. So we can now look at a related problem, the Perseus 1 and NGC 3109 association. We are looking now again at a similar direction. So we see again Andromeda and Milky Way here, now a little bit along a different direction, but we can see these two big planes of the galaxies, which I've just mentioned. And just outside of the local group and parallel to this plane is another plane of galaxies. These are now part of the Hubble flow. They're moving away from the local group, and they are in a very thin plane and moving with the same velocities away from the local group. Now, the problem with this is that it's impossible to get them out. Let me just go back. It is impossible to get them out from here, because a few billion years ago, they would have been in the local group, which is full of dark matter, and they have their own dark matter halos. And so the dynamical friction does not allow them to be ejected by some process which we would not know what it would be, but there is no process we know of which would eject these galaxies in such a way that they move out despite dynamical friction, which is mass dependent, to today form such a synchronally moving group of galaxies in a thin plane parallel to this plane, and this whole plane is receding from the local group. So there are too many galaxies which are receding from the local group too orderly in a plane, and they are too fast. This is impossible if the local group has dark matter, because the dynamical friction would slow or capture these galaxies. Example, if you are underwater, you take a stone, you cannot throw the stone out of the water. So that's basically the visualization of this problem. Now we can go to much larger scales. In fact, as you can see, we are proceeding from small scales up to large scales. We are now going to look at the KBC void and the Hubble tension. So we are now looking at the density contrast. That's the number of, that's the amount of matter as observed in galaxies divided by the mean density the universe has. As we go out to distances of 200, 400, 600 million parsecs, we can see that the density of matter increases significantly. So we are here at 30% of the mean matter distribution, and as we go out, we reach the mean matter distribution at a distance of about 400 megaparsec, which means we are situated in a huge, gigantic void, which is significantly underdense. And this underdensity, this lack of matter nearby, is evident in optical galaxy surveys, near-infrared galaxy surveys, X-ray cluster surveys. We even see it through large scale bulk flows in the form of a CMB dipole. Further, we have strong evidence for highly significant over and under densities in galaxy cluster data here, and also there's a significant exclusion of the cosmological principle based on the distribution of 1 million quasars by Sekrest and Sarkar. And so we can test how likely such an underdensity is in the standard model of cosmology, and how often does such a void occur. So we look at the largest cosmological simulation done, which you can see here is a billion parsec scale. We look at volumes which have the size of the KBC void with a radius of some 400 megaparsec, and we count how many galaxies or how much matter is in these regions and compared to the average density. And we do this many times, millions of times, and plot the frequency of these density contrasts between the density in these volumes relative to the average density. And this is the distribution. So this is the distribution, the frequency of these densities. These are underdense regions, these are overdense regions, and in comparison to the observed void, you can see that the observed void, which has an uncertainty because the observation uncertainties, does not touch the theoretical distributions, and this falsifies the models here in blue by more than 6 sigma confidence. Now, remarkably, this observed KBC void on the scale of 400 megaparsecs automatically solves the Hubble tension, because the galaxies in this underdensity fall towards the sides. We are somewhere in the underdensity, we are not at the center, and so we see locally a faster expanding universe than the average. In fact, the numbers come out just right, as shown in this paper here by Hasselbauer et al., that the Hubble tension is accounted for very nicely. So the Hubble tension actually doesn't exist because the void it's due to this void. However, the KBC void is not possible in the Lambda-CDM model. We can now continue to even further, more distant regions and look at galaxy clusters. So we have the bullet cluster, which is at the redshift of 0.296, has a mass of 2 times 10 to the 15 solar masses. And there are 2 galaxy clusters which fell through each other, collided with each other with a velocity of 3,000 kilometers per second. You can see here the shocked gas from this collision. The mass distribution is shown by these blue regions. And then we have the El Gordo cluster, which is at the redshift of 0.87 with a mass of 20 times 10 to the 15 solar masses. And this is a result of a collision with a velocity of 2,500 kilometers per second. And so the question is, if we start with an initial condition as given by the cosmic microwave background, we evolve this in the computer to within the standard model of cosmology, are we able to obtain such systems in the model universe? And the result is that that is not possible. The observed, especially El Gordo cluster, which is extremely massive, the universe simply does not have enough time by this redshift to grow such galaxy clusters, 2 of them, in fact, and even have time for them to grow and then to fall through each other is not possible in the standard model of cosmology. It is not old enough at this time to have produced such galaxy clusters. So that's a falsification of the standard model of cosmology with more than 6 sigma confidence. So we've seen a whole set of tests which always lead to the same conclusion, that dark matter does not exist, that the whole model actually is dysfunctional. There's never any test which has shown the model to work. Now we can This is a very significant conclusion because it shatters our understanding of the universe in a very dramatic and very fundamental way. So there are additional tests. For example, there's an anisotropy in the Hubble constant from 570 galaxy clusters, which excludes the model at 5 sigma confidence. The dipole in the CMB from our local peculiar motion disagrees at 5.2 sigma confidence with the dipole in quasars, millions of quasars and radio galaxies, as published by Sekres and Sarkar. The CMB anomalies exist, so there's a lack of correlation in scales larger than 60 degrees, and the one side of the universe has more power in the CMB than the other side. There's dust between galaxies, which when the universe was very young would have radiated. It's still radiating today, but today is of course very thin because the universe has expanded. And that radiation from the dust between the galaxies would account for all the photons we identify with the CMB. So if we subtract these photons, it appears, according to Wawrzyk, that there's no evidence for a CMB as a result of a hot Big Bang. Furthermore, the dwarf galaxies in the Fornax galaxy cluster are too perturbed, which means they cannot be protected by their own dark matter halos, showing us that dark matter halos cannot exist around these dwarf galaxies in the Fornax cluster, as shown by Asensio et al. Recently, and most recently, the JWST observations of the very early universe, redshift larger than 10, show us that the galaxies which exist in the universe by that time are already far too massive compared to the galaxies within the standard of model of cosmology. So by this redshift, the standard of cosmology based on dark matter and the merging process cannot grow galaxies to the observed masses. And so we have at least 8 major and independent tests of Newtonian, Einsteinian plus dark matter-based cosmological theories. These cover all scales from kiloparsecs to gigaparsec and even larger. They cover all times from the Big Bang until the present time, and they all are failures. In fact, nothing works in the Newtonian Einsteinian dark matter models according to the tests which I've been involved with and which I've seen in the literature by other teams. To my knowledge, all predictions have been falsified. This is a confirmation of the dark matter crisis research review paper I wrote, which already is a falsification of the current standard of model of cosmology published in 2012. So these newer falsifications only verify and confirm the conclusions reached already in 2012, which is 10 years ago. And so we have a problem. The anomaly is neither the data nor the theories, but it is sociological. The standard dark matter-based cosmological model is the most falsified model which the very vast majority of scientists have ever continued to believe in. Never in the history of humankind have there been so many modern Ivy League educated researchers who together continue to err so badly. This is a completely unique scientific crisis in history. So thus, the whole observed universe disagrees with the Lambda-CDM or standard model of cosmology model. And thus, we come to this conclusion. We've falsified explicitly the existence of dark matter particles based on Chandrasekhar dynamical friction, and so this whole concept has to be thrown out. Dark matter doesn't exist, and the next step is to then be conservative. We can try a model based on GR, and we will say now dark matter isn't there, but the deviations from Newtonian gravitation, to explain flat rotation curves, for example, are due to the quantum vacuum, as suggested by Milgromian in 1999. And so we take now into account Milgromian gravitation or MOND for the density contrasts. We have 2 options. We can now, based on this gravitational theory, keep inflation, hot Big Bang, CMB, and dark energy. This is called the new HDM cosmological model, or we can discard inflation, hot Big Bang, CMB, and dark energy, and that's the Bohemian cosmological model. Why would we want to discard inflation, hot Big Bang, CMB, and dark energy? Because they are all purely speculative, as published by various other authors. These type of concepts like inflation and dark energy are completely speculative. They cannot be tested in the laboratory, and there's no other evidence for this type of physics at all. Plus, there are major problems, like dark energy means that as the universe expands, it's creating more and more energy because of the vacuum energy which is being added to the universe. Plus, the concept that the dark energy actually ripping apart the universe appears unphysical anyway. So we have these two options which we are now studying. The first, what is Mond? If we look at this differential equation, which every one of you will of course recognize, that's the source term. This is the potential. This equation is related to the P Laplacian, well known to mathematicians, which is this operator here. If we have mu equal to 1, we have the standard Poisson equation, just Newtonian gravitation, which is exactly equal to the P equal to 2 P Laplacian. P equal to 2, this term drops out, and we have mu equal to 1. In this case, rho is the matter density and the dark matter density, and phi is then the Newtonian potential sourced by this mass distribution. In Mond, one has this function mu as a function of the gradient, absolute value of the gradient of the potential, like in the P Laplacian. When we are in the strong field regime, so the gradient is larger than this characteristic acceleration scale, mu is basically 1, and we are again back with a P equal to 2 P Laplacian, so we have Newtonian gravitation. If the gradient is much smaller than this characteristic acceleration, then mu is this function, and so you can see then we are at the P equal to 3 Lagrangian, so we P Laplacian. So Mond gravitation basically just means that there's a regime where the P equal to 2 Laplacian is valid, and then a transition to the regime where the P equal to 3 P Laplacian is valid, and this transition is apparently or probably or may be given by the quantum vacuum. In this case, in the new HDM model, we would say that the source term is the baryonic mass plus a sterile neutrino component. In the Bohemian model, we don't even have that component. Now, Mond, we know that Mond correctly describes all observed dynamical phenomena on the scale of galaxies, as nicely shown in this review by Barnick and Zhao. And analytical calculations suggest that the new HDM model correctly accounts for the KBC void, thus there is no Hubble tension. And also automatically we get the L Gordu and bullet clusters in the new HDM model. We know where to go. We are studying the new HDM cosmological model, which is based on Milgromian gravitation. It has inflation, CMB, dark energy, and same expansion history as the Lambda-CDM model. This is work being done in Bonn, Prague, and St. Andrews. We are also looking at the Bohemian cosmological model, which is also based on Milgromian gravitation, but it has no inflation, no dark energy, and it has a different expansion history. And this is being studied in Bonn and Prague. And so to conclude, I will want to show you the simulation, which is a simulation of the new HDM cosmological model. It shows a small box of 10 times 10 megaparsec. And you can see here the expansion factor, which started a redshift of about 100 or 200. And you can see how as the gas cools, the box is expanding, filaments form, and in these filaments we see galaxies emerging with large voids, a large number of disk galaxies which are in these filaments. We even see galaxy clusters forming. And so this is currently being analyzed. What is the distribution of these galaxies? What's the mass distribution? And the first results are rather positive, I must say. So thank you. Hello?
Here we go, Dr. Kroupa. Excellent. So that was a very insightful, very profound presentation. Thank you very much for it. Before we proceed with the questions, I want to ask you one particularly, Dr. Kroupa. You have presented a straightforward
analysis of dark matter trials and or proof-oriented analysis, arguing the inexistence of dark matter. Nonetheless, these tests and trials must have also been seen and reviewed by your peers. What is your perception of their reviews or comments on these tests? Are they finding different explanations, discarding them as flukes, or refuse these propositions entirely?
Well, that's an interesting question. We are getting this published. After all, the scientific journals are meant to publish the results of research as long as the referee does not find technical errors in the presented material. It is tough. Typically, the students who work with me complain how hard it is for them to have these papers published. We do have the feeling that there are double standards in the sense that looking at the literature published, which claims consistency with the dark matter models, those are very often flawed, those papers. I mean, there are many such examples, and it would be impossible to write a counter paper or a rebuttal every time, as we just don't have the person power for that. We have been finding it difficult to publish, and yet it gets published. That is always a critical test of such research that has to be at least passing the peer-reviewed process. Now, once it's published, the question is, how does the scientific community deal with that? And there we are, of course, experience grievous situations. So, for example, there was a huge review on the Hubble tension called the Hubble, I think it was called the Hubble Olympics. I don't know, huge. I mean, I think they had hundreds of co-authors, hundreds of pages reviewing all possible suggestions of how the Hubble tension could be solved, and completely and entirely our work has been neglected. It has been totally ignored. And at a recent conference in Corfu, there was a speaker. The conference was on tensions in cosmology. And the speaker reported on this major review, which was just so acclaimed and amazing and celebrated by the community. And so I put up my hand and asked, "So why didn't you mention the work by Hasselbauer on this, which actually resolves the Hubble tension?" And I don't even remember there was no answer. There was just a lot of words, which to me didn't make much sense. But they find a reason not to cite it, but the most given reason would be that they're simply not aware of that work somehow, or that the KBC vote doesn't exist. But it does show actually that the community is actively not acting on these falsifications. If it were a healthy scientific situation, they would act. They would either show that these falsifications which we've published are wrong, so they would falsify the falsifications,
Right.
but this is not happening. But to ignore relevant literature in such a review, and this has happened not only once. I mean, there are a number of such reviews on the Hubble tension. It's a very popular topic currently, typically our work is always ignored. So ignoring that work is highly non-scientific. So I must admit, I'm myself shaken and very disillusioned by the quality of the current scientific community. So I must, unfortunately, I have to share my sentiments with Ivy Loeb that there's something very seriously broken currently. I mean, if I see an interesting scientific result which poses questions about the theory which I might have liked or thought that it works, and then it shows that this theory has some problems or might even show that the theory is not valid, I get extremely excited. I usually react very positively. I look at the evidence. Can I trust the evidence? Maybe I will try to do recalculations to see if one can probe if the calculations were wrong and maybe write a counter paper. But if one doesn't find a way to falsify the claim that a theory doesn't work, then that claim must stand, and it falsifies the theory, and then that theory cannot be considered unless one really can find that falsification is wrong. And that's scientific progress has completely halted now. It's totally kaput. I mean, the system is not working anymore.
I agree with you that if it was so blatantly wrong, it should be so easily disproved. Putting it under the rug won't make it disappear. And it doesn't really helps the scientific endeavor going onwards.
Well, it does actually help, because what happens is that it's put under the rug, and if somebody doesn't bring it up from under the rug, it will stay under the rug, right? And so as long as I'm active, it's brought up once for a while when I notice that it should be brought up, but typically the community will not bring it up. I mean, there's barely anybody today in the community I know, I'm aware of, who has the backbone to bring up these problems based on the scientific literature. I mean, not speculations, but I've never heard in any conference that somebody would stand up and say, yeah, well, you're talking about the El Gordo cluster as if it works in Lambda-CDM, but then why don't you mention this paper by Asensio as well, which shows that it clearly doesn't work? Nobody would ever do that, because nobody, I think everybody's somehow completely petrified to make a wrong impression in the eyes of the peers, get bad marks, and then not get the next grant or the next postdoc. In fact, getting grants today is much more important than achieving scientific results, because it's the grants which make you important at a university, at least for a brief time. So the time when the grant is announced, you're very super famous. There are newsletters in the university telling what sort of superhero one is. And then it's, of course, all fades away, because the grant is just money and not actual science. Putting science into that then is a lot of work, and usually not much happens, because everybody's trying to show or work in the mainstream to not edge on. I think Avi Loeb has very, very nicely put this, formulated this today in a very eloquent manner. And he has his own experience in a very different field, right, with the problem with extraterrestrial intelligence, which is a completely different field. And I'm surprised that he has voiced these sort of similar or has these similar experiences. I didn't expect that.
Yeah. Yep. Maybe building over the question, there's a question from the chief editor of Science, Analisa Ventola, which I will put on stage. You say that the anomaly is neither the data nor the theories, but it is sociological. As we have just discussed earlier this month, the SSC hosted Chandrasekhar on the topic of panspermia, and he had similar words to say. Could you say more about this sociological issue that also Avilov has echoed in his presentation before?
Well, I think Vikramasinghe has done amazing work, and this idea of what is it called?
Panspermia?
Yeah, panspermia, exactly, is very relevant. It's an excellent scientific idea, makes sense, and one just has to see if there's evidence for it, and so on. It's again, as Avi Loeb has voiced, it's this, I think this analogy of having a lawn and then one flower standing out and stepping on it to destroy it is very, very nice analogy. It's just what people do, especially children, people who haven't yet have such a developed brain. They like to break things because they like to observe. I don't know, maybe they learn from that. Typically children like to destroy, just break something which somebody's built up because it's fun. But it looks like many adults have not grown out of that today. And it's particularly shattering that in the scientific community, this seems to be extraordinarily widely distributed. For me, it is shattering. I have expected a completely different type of environment. I have my own experiences also here in Bonn, unfortunately, but yes, it's why did it come to be like that? Where we would have thought that, especially scientists of the natural sciences related to the physical sciences, should exactly be not like that. We should only draw on evidence and move our understanding forward given the evidence, and departing from known theories if it's necessary. Why is that broken? And I think it seemed to depart around the 1970s. Before that, I have the impression that new ideas were still worked on, and so somebody had an idea, and then part of the community started to work on new ideas if it was thought that these ideas were good. The whole development of quantum mechanics in the 20th and 30s, so the 1920s and 30s, is a perfect example of that. It looked like at that time the scientific community of physics was more or less healthy, And then it started to go very bad. And I think it's related to the concept of competition. It's my feeling that the scientist today is taught by the system and by the successful peers or teachers that one is in competition with others. The concept of competition of ideas is the greatest stupidity people could have thought up in the sciences. You cannot compete for ideas. I mean, either one has a good idea or one does not have a good idea, but you cannot. It's not like it's a race in sports. We have sports people competing for time to run some distance. Ideas is a consequence of intellectual creative activity, and that takes time, and you cannot compete in that level. And some ideas take longer to develop, and they might be much deeper and much better than other shortly, briefly produced ideas. And I think it's this concept that the change of the scientific system into the competitive mode, so competing for grants, competing for awards, which destroyed the scientific process. So today the young people are taught to compete for grants and not for truth. It's more important to win the arguments, and I've seen this in many committees where professors discuss things, and it's more important for many, not for me, but for the majority of the peers I've had to deal with, is to win the argument, even if it's not based on correct statements, because once a decision is made, that decision stands and cannot be, one can't go back. Rather than sitting together as a committee to seek the truth. Seeking the truth has simply faded away. It's not the important aspect of scientific work today. It's the grants, and the bigger the grant, the better. Everybody is working to get grants and the next grant and the next grant, not to actually advance our understanding. Of course, they would claim the idea is to improve our understanding through grants, but that just doesn't work like that. As we've seen, the system has completely failed because I cannot get grants for that type of research. I cannot write a grant proposal to say we need for 5 years, say €1 million to have 2 researchers investigating the Bohemian model to see if we can falsify that model or test it. This is impossible. It will never, ever be granted because there will 2 or 3 very clever referees who will say that it is too speculative, and we know that Lambda-CDM works. And so I think it's the grant system and the concept of competition which has destroyed the system.
I don't have any comments. I don't have your expertise, but I would agree with you in mostly of what you have said, and I won't dampen any of that with my comments. So I will go to another question from our SSC secretary, Mark Irvin, who is asking about your research per se. Other than being ignored, have any other researchers proposed flaws in your models?
Yeah, that's a good question. I wish that would be the case, because then we could react. Maybe there are flaws. I'm not saying calculations can be wrong. I'm not saying that all calculations are always right, and errors can happen, and then they have to be corrected exactly by having a counter paper showing there's an error in that argument or that calculation, and then that would be, if that's correct, then that's great. But that's just not happening.
There hasn't been any counter papers, as you have said.
No, basically none. What does happen is that people would say in a conference, for example, so when I, for example, say, well, look, the Hubble tension is solved by the KBC vote, then they would say, well, the KBC vote doesn't exist. Yeah, and so they deny the existence of a major observed structure, and they are successful with that because nobody else has heard of the KBC void, because it is being put under the rug. I mean, the discovery of the KBC void, which is Keenan, Bauer, and Cowie in 2013, they've gone it looks nearly like they've gone into hiding. I mean, Keenan has gone away from science, and that topic is simply not being much discussed now at all. But it's there. The underdensity is massively there, but it's because it's not being discussed. A person can counter my interjection by saying the KBC void has not been shown to exist, and then the argument is over, even though it's a false statement.
Very interesting indeed. Thanks for sharing. And there are some questions and comments asking about the articles available summarizing what you have said in this presentation. Just to remind the audience that this session is being recorded and it will be available shortly after it's ended, so you can review it later. But also, Dr. Kroupa, can you be so kindly to put some of the links when we finish about some of the articles that you have talked about. I think the audience would really appreciate it. And the other question that we have right now is what are the implications for space travel, if any, given the current state of technology?
Well, yes. So I think it's coming up more and more with this idea of space travel going to other stars. I mean, within the solar system, we are having a fairly advanced capability of doing that, and we can navigate extremely well in the solar system. But going to stars is, of course, future technology. I think Avi Loeb again is heralding that topic in a rather brilliant way. And it has occurred to me that there's a problem that if there were dark matter, which of course there isn't, but if there were, and that's what everybody today, or nearly everybody, thinks there is, then we can't navigate. You cannot go from. You can maybe go to the closest star, which is say 3 light years or light year away. There's not much of dark matter in between in the sense of clumps. But if you want to go, say, to a few thousand light years distance with a spaceship, because you want, say in 100 or 1,000 years, we might be able to do that, assuming we survive. Then you can't. You cannot map out your course if you are still stuck in the dark matter framework. It will not be possible to know which course to take, which means you'd have to build a ship, which you probably can't do because it would have to be. You'd have to carry so much surplus fuel with you just in case there is a particular subhalo, dark matter subhalo, in the way or offside somewhere to counter that, and you'd never know when you would actually arrive because of this problem. Now, in Milgromian gravitation, that's completely like Newtonian gravitation. It's exactly calculable. So if I were an astronaut and would have to go into a ship tomorrow to go to a star 1,000 light years away, I would program our computer using MOND, Milgromian gravitation, and I would throw out from the ship anything to do with dark matter. I would only use Milgrom because that is predictive, and I trust that.
Very interesting insight. Thank you very much. So I think that will be all for this session. Thanks to all for coming, and to you especially, Dr. Pavel Kroupa. This has been a really wonderful and insightful presentation with a lot of insights about the state of the science and where there are some opportunities that that we as a field or the field as a general could try to push onwards.